Okay, so in doing this problem here, I know that this says dx dy dx, tangent x is equal to tangent y. I'm going to change my variables around, and I'm going to divide by tangent of y, 1 over tangent y dy is equal to 1 over tangent x dx, doing some algebraic manipulation there, and I'm going to take the integral of both of those. Now part of my problem is I don't actually know the integral of tangent y, but I know 1 over tangent theta is 1 over sine theta cos theta, which is cosine theta over sine theta. So I can rewrite this line here as cosine y over sine of y dy equals to cosine x over the sine of x dx. And so in doing this now, what I want to consider doing is thinking about a u substitution. I know that the derivative of sine is cosine. So if I'm going to let u equal to sine y, du is equal to cosine y dy, and I can do that substitution. So that means that I can say 1 over u du, because cosine y dy is here and the u is there. Similarly, if I can say the same thing like v dv, not using u because I know it's not exactly the same. So when I integrate this side, then this ln u, which I know u is sine of y. Sine of y is equal to ln sine of x plus c. Getting rid of the natural logarithm, I get raise it to the power of e. I get sine y is equal to sine x times e to the c, which I know this is just a constant, so I'm going to make that some constant a. So I also know my initial condition is 2 equals 2. So I know then that sine of 2 is equal to a sine of 2. So a is equal to sine of 2 over sine of 2, which is equal to 1. So I know I have sine y is equal to sine of x. So at this point, I have to recognize that y and x are angles. And so I also know that sine of y is going to equal to sine of x plus 2 pi or 4 pi or 6 pi n, where I know n is an integer. It can be positive or negative integer. It belongs to z. And so then I can say that y is equal to x plus 2 pi n, where n is an integer value.